we embark on the journey of the graphs for sines and cosines, and kind of continue to elaborate on this triangle that moves through this circle as we spin around the unit circle. We mentioned this reference angle yesterday, and how that this reference angle helps us create these triangles that we get when we spin around into the different quadrants. There are some rules for reference angles. Again, kind of more memorizing. You're going to find the second half, we do a lot of the stuff we have to memorize. There are some rules that will be very helpful for you to know when it comes to finding multiple answers for some of these trig functions. Like, you're going to eventually get to the point where I'll say, tell me what the two angles are that give me a value of sine that's equal to 1/2. And you're going to be able to say, okay, well, I'm still in quadrant 1 and 2, and that happens at a 30-degree angle and a 150-degree angle. So that would happen. And all of that has to do with this concept of a reference angle. And so what a reference angle is, it's an acute angle that's measured, and this is the key part of this part that we don't want to get messed up. It's always measured from the x-axis, never from the y-axis. Always coming from the x-axis to the terminal ray of wherever my triangle is. Now, in quadrant 1, as in this case right here, the reference angle and the theta that we are turning to get to the terminal ray, they are the same thing. So between 0 and 90 degrees, your theta and your reference are equal to one another. The triangle that I would create in there, you can kind of envision. There's my triangle right there, right? In quadrant 2, what we did is we rotated ourselves past that 90 mark, and now we're over here in the quadrant 2 area, and again, thinking about the triangle that would be created from something like this. There it is right there. There's my triangle. When we were doing this stuff yesterday, we labeled the parts of those triangles, and we said that this thing has a negative x value and it has a positive y value. But now we're just going to focus on simply the angle. So theta took us from 0 to that terminal ray, and now we're going to relate that theta in terms of a reference angle. So looking at that, you guys sort of come up with a formula that allowed you to calculate alpha, which is what our reference angle is. What would I use? How would I find alpha if I had that situation in quadrant 2? 180 minus. Yeah, exactly. So a theta angle, or an alpha angle, a reference angle can be found in quadrant 2 with this rule. Now, we're using degrees, but I could be using radians as well. So that could also be pi minus theta. 180 minus my angle of theta gives me some acute angle that's here in quadrant number 2. All right, we just keep applying this concept all the way around, so we get all 4 quadrants involved. What's the rule going to be here for quadrant 3? So here's my theta, spins me to there, gets to the terminal ray. How do I find what's left over there? How do I get back to the x-axis? What? So if we're trying to write a rule, for the reference angle, how would I find that? Well, 180 is involved, but I'm not adding 180 to it. I'm actually subtracting 180 from something else. What am I subtracting it from? Theta. So theta takes us all the way to the mark, and I want to back up. I want to spin negative rotation-wise. I want to subtract from that the 180. So if I've gone all the way around, and then I remove from it 180 degrees, I will find what's left over here from for my alpha. So there's my rule for finding reference angles in quadrant 3. Now remember, we're writing rules that involve calculations of reference angles, but I could take any of these, and let's say I knew what my reference angle was, but I wanted to find theta. I could take any of these and solve for the different variables. All right, and then over here, quadrant 4, what's this one have to be? 3 360 minus what? Theta. Okay. So alpha here is all the way around and remove theta. So 360 degrees minus theta. So there they are. Those are our 4 rules for finding reference angles in all quadrants. And again, every one of these, you're always measuring to the x-axis, to the x-axis, to the x-axis. Not going to the y. Remember to create my triangles going to the x now. All right, so let's see if we can identify some reference angles here. We good on those rules? Everyone have that down? Okay. All right. What are the reference angles for these things then? 120 degrees, 150, or 250, 340, 70. Visuals, right? For those of you who like to see where you're at. So 120 degrees, I'm over here in quadrant number 2. So there I am. There's my theta. So I am asking you to identify what's the leftover or what's the alpha in this case. Then we just use our rules. Once I know where my angle puts me quadrant-wise, I just use one of those 4 rules. And this rule says that alpha needs to be equal to 180 minus theta or a 60-degree reference. 60-degree reference. Yes, probably handle the rest of it. 250. What's the reference? 70. 70. Very good. 250, you're in quadrant 3. Quadrant 3 rule says that alpha is equal to theta minus 180. So 250 minus 180 takes me to a 7-degree reference angle. All right, how about 340? 20. Quadrant 4, where it says I'm going to find by going 360 minus theta, so 360 minus 340 would put me at 20. And then how about D? 70. When you're in quadrant 1, that is your reference angle. I'm gonna show a little bit differently besides the angle thing. Let's look at the triangle part of this thing. So let's take a look at 250. 250 is somewhere, I don't know, right about there. And if that's the 250, and I create out of it this triangle. And we said that alpha, because we're in quadrant 3, needed to be 250 minus 180. And that's how we got the 70 degrees. And there's my 70-degree mark. Well, what happens really, what we're doing is we're taking a triangle that I could have in quadrant 1, and we're repositioning that triangle in other quadrants. So I can take this same triangle right here and put it in quadrant 1. Look like this. There's my 70-degree angle. Same triangle. But just flipped over the y-axis and then flipped over the x-axis to create this triangle that we have down here in quadrant. So that's another way to think about your reference angles. Repositioning the same triangle in all 4 quadrants and seeing what you get for this thing. You have any problems with those, folks? Seem pretty simple? Pretty straightforward, right? All right, so I think one of your homework problems is something like this. Express some value, cosine, sine, theta, some angle in terms of a reference angle. We're going to kind of think about it along the lines of that triangle that's in quadrant 1. So the first thing you want to do on this is recognize where the angle puts you. Want to know where I'm at. I'm always trying to find where I'm at. We'll worry about the cosine part of it later. Let's just worry about where you're at. So 533 degrees. Anyone guess where we're at for 533 degrees? Quadrant 2. Because we've gone around a full circle, we've got 360, and then we've gone around, what, 173 more? So we've almost put ourselves back onto the x-axis over here, but we're not quite there. So in terms of a terminal ray, I've got something that looks like this. And how we got that was we went around, once, and then we kept going another 173 degrees. So that's how we got 533.
There you go.
That's what I'm thinking. All right, so what's my theta then? Well, I already said that that red angle right there, we went around 360 and we had to add to it 173 degrees, so that's my theta. And that means I can use my rule. Here's my alpha. Alpha in quadrant 2 says to go 180 minus your theta. So we have a 7-degree referencing. All right, now let's go look at the cosine. So over here in this world, thinking about this, ASTC, what's the value of cosine over there in quadrant 2? Negative. The only thing positive over there is sine. So cosine is negative over here at 533 degrees. So we have that the cosine of 533 degrees is actually equal to the opposite of a cosine of 7 degrees. They have the same referencing. 533 and 7 is the same thing. So if I, again, referring back to quadrant 1, if we're always thinking about quadrant 1 for my triangle stuff, 7 degrees reference angle. To make this cosine of 7 equivalent to the cosine of 533, I have to put this negative in front of the cosine of 7 to make this become a negative cosine value. Because if I just punched in the calculator right now, cosine of 7, I'm going to get something that's positive. But because this is negative, that means I have to stick a negative in front of that cosine value to make it in terms of a referencing. I think you have like 1 or 2 problems for that. So basically, just go use our rule, find out where your reference angle is, determine if I need to be a negative or a positive value of that to come up with the same thing. So if this said sine of 533, quadrant 2 sine would be positive. If it said sine of 533, then I would have made this. Sine of 533 is equivalent to sine of 7. They're both positive. So there's a couple, 1, 2 of the problems for tonight. Let's try these other 2, or you guys try these other 2. So thinking about that in terms of a reference angle, what would I be for sine of 122 and the cosine of 5? See if we can express them in terms of a reference angle. So 122. So in this world over here in ASTC, we know that sine is supposed to be positive. So sine of 122 being positive is the same thing as a sine of 58 degrees. Both of those are positive values. How about cosine 5? What's that the same thing as? Cosine 5, yeah. That is a reference angle itself, so there's really nothing to find right there. There we go. Same, all same. Questions on reference angle stuff? Really? How do we graph them? Oh, okay, so cosine of 5. Oh, wait, I didn't even pay attention to the fact that that's not a degree. We don't have a little degree symbol on that. So this is actually a radian. So cosine 5, thinking about radians, oh boy, now you got to do your conversion in your head. Where are you going to be if you're at 5 radians? Think about how many radians is it to go around all the way. 2 pi, which means 6.28. So I'm not quite there to 6.28. So somewhere over here is where I'm at. Thanks for pointing this out. I didn't pay attention to the fact that there wasn't a degree symbol. Did you guys think it was degrees also? Yeah, sorry about that. So if it doesn't have a degree symbol, it is a radian. So that's where we're at. We have a theta radian angle of 5 radians. And it puts us over there in quadrant number 4. So how do we go about finding the equivalent reference angle for radians? Well, it's the same concept. In quadrant 4, we said it was normally 360 minus your theta. But now we're talking about 2 pi minus your theta. And because we have a radian given to me in decimal form, we're going to convert 2 pi to decimal form and get 6.28 minus 5. Means I have a reference angle of 1.28 radians. Okay, so we know that's my reference angle. However, thinking about this, the value cosine is positive in quadrant 4, which is good, because it's also positive in quadrant 1, where I would have a 1.28 reference angle. So cosine of 5 radians is the same thing as the cosine of 1.28. Yes?
How do you know if the answer is going to be positive or negative?
You go, first of all, with where the angle puts you. And then after you're at that spot, you look at the value of sine or cosine. And you think about, in quadrant 1, sine, cosine, tangent are all positive. In quadrant 2, it's only sine. In quadrant 3, it's only tangent. In quadrant 4, it's only cosine.
Oh.
So you put yourself in the right spot, then you use all support the covers to figure out what your place is. Yes?
Where do you figure out where to put the radian or the radius line coming out?
Where do I figure out how to put that guy in there, the terminal ray? That has to do with your angle.
But how do you know the 5 is?
Right. So we're not so familiar with the radians. So here's what you could do. You could convert that to degrees with my 180 over pi, and then tell me where I'm at. Eventually, though, you're going to get to the spot, like we were asking earlier, am I going to have to memorize this? You're going to know that 2 pi is the same thing as 6.28 radians. And so you'll be able to judge where you are at for decimal radian answers. 1.57 is the radians there. 3.14 is the radians here. 4.71 is the radians here. And then 6.28 is the radians there. So I could take all my degree numbers, convert them to radians, and then I can get an idea of where I'm at. That's a good question. All right, trig tables. You guys are familiar with this? You're not familiar? Oh, yes. Okay. Stretch
So,
the entire.
no, for your answer, would
Yeah.
you put down cosine 1.28 or would you
Uh-huh.
put down just the, what's it called?
I don't know.
Those are little fish, that's simple.
Oh, the fish, the alpha.
Yeah.
No, in these problems where it says express what you've been given in terms of a reference angle, you're going to write the answer as whatever the trig function was, cosine, sine, tangent, and then of the new angle that puts me at the same value of the one that's been shown. So this is a negative cosine. That meant I would write negative or sine or cosine of negative, where is it right here? Negative cosine of 7.
Okay. Wait, why did you circle the message?
I did. I didn't circle it. I don't know why. I just didn't. right, so in the back of your book, you want to peek over there. 805 begins all of your trig tables. However, your calculators are probably going to be faster for this. But you can find in there all of the values of sine, cosine, tangent. I think it even does cotangent, secants, and cosecants for your decimal degrees and your radian. It gives you the ratios already. But it's probably just faster to use the calculator. All right, we doing okay so far? All right, right triangles. Now I'm thinking that this did happen in geometry. Did you guys? Yeah, pre-calc we kind of hammered this, we beat it to death. But in geometry, for those of you who came from Algebra 2 right here, did you talk about special right triangles? Okay, good. So this should be review then. Hopefully it's going to be review. There are two of them, the 45, 45, 90 and the 30, 60, 90. And what makes them special is those angles, 30, 45, 60s, those are our special angles that we're going to those are the ones we're going to memorize on that circle. Remember that first day we looked at it and said, you guys are going to know this stuff by the end of this first two chapters. These two triangles create all of those special values. What makes them unique is their ratios, their sides of the ratios is what makes these triangles unique. So in the first one, it's an isosceles triangle, a 45, 45, 90, which means that the legs are going to be the same, and then the hypotenuse is going to be something bigger than the legs. Now, these are your probably most common relationships, 1, 1, and square root of 2. You could, however, change them, knowing that they're always in this proportion to one another. So that means, what if I were to make this equal to 2? What would these legs then become? What would they become? Square root of 2? Is that true? No, I'm just asking, is that true?
Yes.
Square root of 2 squared plus square root of 2 squared. What do I get when I square root of 2? 2. So 2 plus 2 is 4, and the square root of 4 is 2. So you can adjust any one of the sides. Just make sure you adjust the other ones proportionally. So anyway, the ones that are given, the 1, the 1, and the square root of 2, those are your most common. When we write these proportions, though, we want to make sure that if I have denominators that have radicals in them, I always rationalize them. All right. And then for your 30, 60, 90, how do you remember which side goes where? It's always just go in order of small angle to small number, next biggest angle to the next biggest number, and then 90 is always the 2. So 1 and 30 go together, 60 and root 3, and then 90 and 2 always. Okay, so how do we use these? Well, we use them to find these exact values. So our calculator, no calculator portion of our quiz would be involving stuff like this. Find exact values, meaning I don't want you to punch it in and give me a decimal equivalent. I want radical form or just the integer that you would get here. So what am I asking you for? I'm giving you a sine or a cosine or a tangent of some angle right now. And I'm asking you to tell me what's the relationship of y over r or o over h. That's what I'm asking you for, is this. I want to know what's that relationship for this given angle. So here's where you're going to get good at transferring your knowledge from radian mode to degree mode back to radian mode. This is where you're going to get good at it. 7 pi over 6. Pi over 6's, remember, are 30-degree increments. 6 pi over 6 put me at pi, which is 180. And I kick down one more pi over 6 means I'm adding 30 degrees to 180, so this is a 210 angle. Degree-wise. So again, I'm the visual person. So where am I with 7 pi over 6? You're right here. There's my triangle. That's 7 pi over 6. But what we need out of this is not the fact for 7 pi over 6, we need the alpha. What's the alpha of a 7 pi over 6? What is it? It's a 30 degree. I already told you that. Think about it, though, in terms of, remember our rule? Pi minus theta. So we have, I'm sorry, this one is quadrant 3, so this one is theta minus pi. So we have 7 pi over 6 minus a pi, or a 6 pi over 6, giving me a reference angle of pi over 6, which, yes, is 30 degrees. So you're going to need to know both. If I give you information as a radian, I want my answer with radians. If I give you information in a degree, I want my answer in degrees. So what is the exact value for the sine of 210 degrees? Well, we know where we're at. We look at all support the covers, and I determine that sine is supposed to be a negative answer right there. Now I go and check out the triangle that goes with this reference angle. So this triangle is a 30 angle, so I'm going to go back and take a peek at the 30, 60, 90 triangle. So we're looking at this guy right there. Here's where we're at. You don't have to, if you want, you can flip the triangle around and put it in the right spot. I don't care. But you don't have to. Just know that if I'm talking about the sine of a 30 degree angle or the sine of a pi over 6 angle, that is going to create a relationship of O over H or Y over R. It might be easier for us to think of O's and H's because we're back to a triangle versus our unit circle. Well, what is my O over H relationship? We're at 30. 1 over 2. So the 30 degree angle creates an O of 1. And then a hypotenuse of 2. So this is a 1 over 2 relationship. But now I got to go and remember that it's a negative sign. So I'm in here in negative sign world. So the answer to this is negative 1/2. So we're using our triangles in the right quadrant, figuring out what I'm looking for, determining if I'm supposed to be positive or negative. So now we're kind of compiling all the previous 3 sections we've done up until this point, and we're blending them all into one thing right now. Yes?
So then theoretically, the cosine of 60 would be root 3 over 2, right?
The cosine of 60 would be 1 over 2. Yeah. We're going to find that out. Those are called co-function relationships. That the sine of 30 and the cosine of 60 are the same thing. They're the same idea. Right? Because if you look at cosine here, Jeff, right? Cosine adjacent hypotenuse. So yeah, those are called.
So then the sine of 60 would be
root 3 over 2. Yep. Yep. Those are wrong.
Well, okay, so this with my typical answer for the cosine of 60, the square root 2 over 2.
For the what?
Cosine of 60.
Cosine of 60 should be 1/2.
1/2, yeah. The book says it's the square root of 2.
Are you sure you're looking at 60 and not a root 45? You might be looking at a cosine of 45.
yeah, no, it says, because it's for the cosine of 60.
Just stop.
Jeff, just stop.
I know what it is.
So the answers, what do we do here? So log, first of all, cosine 7 pi over 6. It's in the same location as this one was. So we had a 30 degree reference angle. And we know for cosines, going back to our triangle, cosine is an adjacent over a hypotenuse. So 30 degrees, there's my adjacent, there's my hypotenuse, it's going to be square root of 3 over 2. But because we're in quadrant 3, where cosines are negative, my answer should be negative root 3 over 2 for that. The next one, we got a log base 4 of sine 150. So sine 150 is what we need to look at first. So put ourselves in our little sketch. Here's 150 degrees. means I have a reference angle that's equal to 30 degrees again. And thinking about what sines are over here, they are positive. So far I know I'm going to get a positive solution there. 30-degree reference angle, we saw it over here with part A, was a 1/2. So now what you've got is a log base 4 of 1/2. And so now we're going to switch our forms, right? 4 to some power equals 1/2. Let's go back to chapter 5. 2 squared to the x power equals 2 to the negative first power. So 2x equals negative 1, or x equals negative 1/2. The sine of 50 is equal to 1/2. Yes. All right, next two. 135 is over here, quadrant 2. Reference angle is going to be 45 degrees because of 180 minus theta. I am in negative cosine world. So my answer that I'm going to get, I automatically know is going to be negative. And then I just got to go look at my triangle. So back up to my 45 for a cosine. Cosine of 45 is adjacent over hypotenuse, which is the same as the sine of 45, which is 1 over root 2. Now here's where we're going to want to rationalize. So if a cosine of 45 is 1 over root 2, it's the same thing as root 2 over 2. Multiply top and bottom by square root of 2. And that is what this answer is. You guys get that? Yep. Why is negative? All support the covers. Quadrant 2, cosine negative.
Okay, how'd you get from 1 over radical 2 to negative 2 over 2?
Okay, I didn't get to the negative 2 over 2. The negative comes from the fact that I am negative at the cosine
I
point.
got that, but I had 1 over radical 2.
Okay, so
Negative 1 over radical 2.
you had that?
Yeah.
Okay, negative 1 over radical 2 is not rationalized.
Oh, with the rest.
So we need to rationalize it by doing this. Yeah. All right. So far, so good? Jayleen?
For the triangles, how do you know which leg is opposite?
Okay, how do I know which leg of a triangle is opposite and which one is adjacent leg? I think food often. So if you're hanging out at an angle and you want to know what the opposite of it is, think of the angle as your mouth. Here's my mouth. And my mouth always eats the opposite side. Now, along with the hypotenuse, the roof of my mouth, the adjacent side also forms the other side of my mouth. Hypotenuse is always the part across from the 90 degrees.
Yeah. Wait, okay.
Is that a good visual for you? Probably. Anyway. Sine of 330. Quadrant number 4. There's 330. A lot of 30s. So that means a reference angle of 360 minus 30, which is also 30 degrees. All support the covers means sine is going to be negative down here, so my answer is going to be negative. We already know from our previous ones that the sine of 30 is 1/2, so this answer is negative 1. How do we do on those? We get them? Ish? Get them ish? Okay. Questions? Yes.
On the quiz tomorrow,
Yeah.
are the reference angles ever going to not be 30?
So the graphs of sine and cosine, here we're going to take a look at our first look at the graphs of sines and cosines. Sine. Let's talk about sine graphs. Sine, if we think about our unit circle, Sine, we said, measures the y value of a point as it spins around the unit circle. Cosine, we said, measures the x value of a point as it spins around the unit circle. So here's a cool little ditty that shows us this relationship between sine and cosine. So here we're going to see, you guys see that okay? On the left-hand side of these little diagrams that are rotating is the unit circle itself. And on the right-hand side is the graph that you generate from moving that point around the circle. So on the top graph, you see the red bar, which is showing the y value of the point, and then the graph is showing you that y value as it goes through its full period, which is once around a circle or 2 pi. And then on the bottom, you're seeing the cosine doing the same thing. Now notice the curves are different. They're actually off by what we call a phase shift. They're off by 90 degrees from one another. The sine curve starts at the origin, and then it goes up. The cosine curve starts at 0, 1, and then it goes down. But we looked at that actually with the last homework problem. You were asking, where am I increasing, where am I decreasing? So you're watching the cosine curve, and you got the green bar telling you my x value. The weird thing about cosine is you'll notice I'm plotting the x values, though, on the y-axis, which might be a little confusing. But we're plotting, again, the horizontal distance from the origin for cosine is what we're plotting here for this curve. Those good little visuals for you? Kind of get an idea of what we're doing? Yes? No? Maybe? Yes, those are good visuals. Is this going to be on, what do you mean? No, yeah, it is on today's lesson. All right. So that's what we're doing. What?
Today's lesson.
Oh, no. Today's lesson. No. Sorry. All right, so here they are. So cosine. This is the shape you need to know for cosine. I want you to know the shape through one, it's called a cycle. Through one cycle, I want you to know the shape. A cycle is a repeated pattern. Hey, a repeated pattern. I see that pattern repeated every 360 degrees. So a cosine curve starts up, goes down. That's the pattern I need you to memorize. Now, if we look at this curve, we can actually see the quadrants represented here for my unit circle. There is quadrant number 1. Here, that's quadrant number 1. Here is quadrant number 2. And so on. Quadrant number 3. Quadrant number 4. So we can see the values of, in this case, x, as I move along my unit circle in the different quadrants. X is equal to 1 at y equals 0. There it is. At 90 degrees, cosine is 0. At 180, cosine is negative 1. And then so on through our curve. You good, Alexis? You see it? Now, if I took that curve right there, that blue highlighted area that I just drew, and I moved it to the right 90 degrees, oh, that just sucks. Oh, man, that's not working. I wanted to grab just the curve, but that's not going to fly. If I took that blue curve and moved it to the right 90 degrees, and then added some stuff, so if I imagine this part of the curve right here, move it over to the right 90 degrees, I create this guy, the sine curve. The sine curve, same thing. Break it into its quadrant parts. Pi over 2, quadrant 1. What happens when I'm at 0? Sine is equal to 0. What happens when I'm at 90? Sine is equal to 1. Back at 180, sine is 0. 270, sine is equal to negative 1, and so on. So those are your two curves. And I need to know these general shapes here. That's horrible that it's yellow.
That hurts.
Can't even see
I
it.
now have a headache.
Okay. Okay, oh, I apologize for that. Got accepted written all over.
Workers' comp.
All right, so what are we going to do?